Now, wanting the SI session implies I am going to the SI session.
All day together on Friday. Yes, I thought. Okay, cool. Also, next Wednesday, there might be food. So if you want to go, I need to know Tuesday how many people will be there. Otherwise, people are going to get like a bite of food.
Next Wednesday.
I'm going.
Next Wednesday?
Day, 10:23.
Yeah, I believe it is.
I assume that's why those are food.
Yeah.
No, it was just kind of like I felt like bringing food.
Oh, well, you timed it right.
Okay, cool.
We don't need
So,
moles.
By Tuesday, I need to know attendance for Wednesday, because otherwise, like, you guys are gonna have to share food. You know,
Joey doesn't share food.
Joey doesn't.
Okay, so there won't be a session tomorrow then.
There will be a session.
There will be one tomorrow. Friday I don't have mass, so it's like,
You wanna come home? Yeah, last week we for the exam room.
Okay.
YouTube video.
On the
For that slice of
lab I just handed back, a couple of things that are worthy of comment. At least, so says me. Some of you were, and I know part of this is just nervousness on first lab, but some of you gave me a little treatise on the purpose. A little treatise on the purpose can be okay for a formal lab report, but for your lab notebook, short and sweet. All you really needed for the purpose of this lab was to purify a sample of acetanilin. Done. That would have been perfect as a statement of purpose. And some of you said purpose was like to obtain a melting point. No, that was definitely not the purpose. Yes, we obtained the melting point, but for the purpose of determining the purity. The purpose of the lab was to purify the acetanilin. The obtaining the melting point afterwards was just to see if we were successful at doing so. So the purpose wasn't to get the melting point. The purpose was to get pure acetanilin. What else? Some of you, at no point did you say whether that purpose was fulfilled. We were taking the melting point for the purpose, and this was one of the pre-lab questions, why are we taking the melting point? We were taking that melting point for the purpose of determining purity. And the main thing about determining purity via a melting point is the range. Always report melting as a range, from where the stuff first starts to melt to where the stuff is completed melting. So we say melting point, but we always mean a range. And a narrow range is indicative of purity, which some of you commented on. Yay. And some of you just kind of let your melting range just kind of sit there without comment. Somewhere in a conclusion, I think it screamed for comment. The acetanilin was or was not successfully purified based on this good or poor melting range. And on most of your labs, I wrote lit value. My little lit, it's kind of hard to see. Even I look at it, I'm like, what am I saying there? But what that means is lit value, short for literature value. You know, it's very helpful to know what the accepted melting point is of this substance, of the acetanilin. Most of you just kind of threw a melting point out there with no comparison to, you know, what would be expected. That it was not super critical in this lab. So I guess what I'm saying is that you should always, you know, compare what you got to what may or may not be known about the substance. Not super critical in this lab because we knew we had acetanilin, so we weren't trying to identify the substance. We weren't interested in the melting point per se. other than if it was wildly different from what acid analyte is supposed to be. You had to, stroke your beard and say, do I even have acid analyte? The main thing about the melting point in this lab was the range. But in other labs, where you're synthesizing something, I don't know, like maybe the second lab, we're synthesizing something. If we're taking a melting point, not just as an indication of purity, yeah, it can help us determine purity, the narrowness of the range, but in this case, it can also help us identify the substance, i.e., did you make acetaminophen? The only evidence you're going to have as to whether you did or did not make acetaminophen is if the melting point that you get matches up with the known melting point for acetaminophen. Make sense? What else I got to say? I think that might be it. Yeah, that's about it. Any questions on that? Okay. What were we talking about last time? We were talking about stereochemistry. We saw that in the broad category of isomers, there are constitutional isomers, there are stereoisomers. Among stereoisomers, there are enantiomers, there are diastereomers. We talked about enantiomers specifically. Enantiomers arise when we have compounds that don't have a plane of symmetry. Anything that does not have a plane of symmetry will have a mirror image that is different from itself. It'll be an enantiomeric relationship. We often call that property chirality. You are said to be chiral if you have a mirror image that is different from yourself. And the famous example, in fact, the origin of the word chiral is a hand. A hand is something without a plane of symmetry. Therefore, its mirror image is going to be different from itself. And we saw that as it relates to organic compounds, if you have an sp3 hybridized carbon, i.e. a carbon that has tetrahedral geometry about it, if all four things bonded to that carbon are different, and only if all four things bonded to that carbon are different, that molecule will then not have a plane of symmetry and therefore will have a mirror image that is different from itself. Rock and roll. We saw with cis-trans isomers, for example, if we look at this guy versus this guy, the first one is 1,2-dibromoethene, the second one is 1,2-dibromoethene, but they are different molecules, they therefore needed different names. So we had to, in front of the name, add cis or trans as appropriate to distinguish among the isomers. Well, the same thing is true with enantiomers. They are different compounds. Yes, they have the same chemical properties. All the chemical properties are going to be the same, except for their reactions with other enantiomeric pairs. But that's a difference. They are different compounds. They're separatable, not easily, but they're separatable. They are different compounds, so they therefore need different names. We name a pair of enantiomers using what is colloquially called the RS system. It is more formally called the Kahn-Ingold-Prelog system, named after three characters who developed it. Here's the thing about the RS system. We in this class could sit down and come up with a different system for naming enantiomeric pairs. could be just as logical as the Conning-Gold-Prelog system. And we could talk to each other just fine with our invented system. But we couldn't talk to anyone else on the planet. We want to be able to talk to other people on the planet. So there is an internationally agreed upon way of naming enantiomer pairs, and this is it. So I always get people who say, well, why don't we do it this way? My response is going to be, yeah, we could have done it that way, but we didn't. Because that's the only response I'm going to be able to give to that question most of the time. Unless you suggest it doesn't make sense. But most of the time, people say, why don't we do it this way? They're presenting something that makes just as much sense. But it's not what was internationally agreed upon. Okay, so. If I look at something like that, can I even play the game? Can I hold that up in front of a mirror and look at the molecule that's in there? No, I'm not showing any three-dimensionality. Do I have a chiral carbon in this molecule? Nope. I have a carbon with 4 different things bonded to it. So I know that this molecule is capable of enantiomerism. I know that there are 2 different molecules that that structure represents. But I can't say anything about which one this may or may not be. I can't tell you if that's a left-hand glove or a right-hand glove. Okay, because I'm not showing any three-dimensionality. Enantiomerism is all about differences in three-dimensionality. Maybe now's the time to make the following statement. Being able to think three-dimensionally is going to be very helpful here. That probably comes as an obvious statement. Of course, that's going to be helpful here. To be able to think three-dimensionally. Some of you are going to be quite good at it. Some of you are going to totally suck at it. Three-dimensional thinking is kind of famous for not necessarily correlating very well with other academic talents. So if you think of yourself as an academically talented person, you may fall flat on your face with this stuff, thinking three-dimensionally. If you think of yourself as someone who kind of struggles to keep up academically, you may have a hard time wondering why everyone isn't getting it. It's obvious. You might be thinking. If you're good at thinking three-dimensionally, don't be smug about it. There's nothing that you did for yourself. You just got lucky. If you're bad at thinking three-dimensionally, don't get down on yourself. There's nothing you did wrong. You just got lucky. And as with a lot of other things, life is going to be easier for those who are good at it. Life is going to be harder for those who are not good at it. That's life with all sorts of things. In this class, you will always be able to use models. Any quiz or test in here, you will always be able to use molecular models. Some of you are not going to want to mess with those molecular models. It's going to be easier for you to not have to deal with it. Some of you are going to use them like a crutch. I would strongly encourage all of you to try not to need them. I said try not to need them. That's not to say you can't use them. Try not to need them, but use them to the extent that you need. Okay. So, in order to even talk intelligently about enantiomerism, we have to be able to represent things three-dimensionally. There are a couple of conventions. Here's the most common. Obviously, we need a carbon in the center. There's going to be tetrahedral geometry around that carbon. Tetrahedral geometry, as we know, is inverted perpendicular V's. One of the V's we can put in the plane of the paper, in the plane of the whiteboard. So I've got something bonded up here, something bonded up here, down here. Given that, where's the other V? In other words, where are the other two things that are bonded to this guy? Yeah, one has to be coming out towards us in front of the piece of paper or whiteboard, and the other has to be going back behind. So we've already commented on this little wedgie. And it's showing, oh, it's coming towards us. The notion being, you know, here's the bond. It looks bigger here because it's closer. And then the other is going back behind us. So here's our 1V. Here's our inverted and perpendicular to that V. That is the most standard way. Okay, so now I can throw these things around. There's a bromine, say there's a chlorine, let's say there's a methyl group, let's say there's an iodine. Now I'm showing three-dimensionality. I can look at this guy, and he's going to have a mirror image that is different from himself, because he has a chiral carbon. I could pretend that there's a mirror here. In that mirror, I would see this molecule. The bromine would be up here, the chlorine would be here, the methyl group would be here, the iodine would be back here. These are two different molecules. They're pair of enantiomers. They're a pair of enantiomers not because they are mirror images of each other. They are a pair of enantiomers because they are different molecules that are mirror images of each other. They're a pair of enantiomers because they're molecules with a chiral carbon that are mirror images of each other. So they have to have different names. I mean, they're both going to be, you know, one bromo, one chloro, one iodoethane. So we got that much going for both of them. One bromo, one chloro, one, can't write today, iodoethane. With cis-trans isomers, we put a cis or a trans in front of this to distinguish who's who. For a pair of enantiomers, we put an R or an S in front of this to determine who's who. And here's the game. Rather than sort of give you a list of rules, you can go into Solomon's, get a list of rules. Let's just do it. The first thing you do is assign priorities to all four things around the stereogenic carbon. You assign priorities based on atomic number. Atomic number of the atom bonded to the carbon. So we have an iodine, we have a bromine, we have a chlorine, we have a carbon. Which one of these has the lowest atomic number? You shouldn't even have to look at the periodic table for this one. Carbon. It gets the lowest priority. Which one has the highest atomic number? Iodine. It gets the highest priority. Which one has the second highest atomic number? Bromine. Point number 3. What the Kahn-Ingold pre-log system says, and appreciate that if you have a tetrahedral gig, you know, here's a carbon with 4 things bonded tetrahedrally around it. You know, we talked about the inverted V game, but another game, another way to look at a tetrahedron is, you know, here's your central guy kind of sitting on a tripod of 3 atoms with an atom on top. Or you can look at it this way. Here's your central atom with 3 guys coming out at you with 1 atom behind. That's one way you can always look at a tetrahedron. You guys looking at me funny. This is okay, right? So like carbon on a tripod with a atom on top, or have that tripod pointing towards you. Well, in the Con-Ingold pre-log system, this is how we look at the molecule. We put a guy behind, which necessarily puts the other three guys coming out at us. The guy we put behind is the guy of lowest priority. Once we put that guy behind, then the other three guys are going to be pointing towards us. So let's say the white guy is the guy of lowest priority. We look at the molecule with that behind the central carbon. The other three guys are coming out at us. We go from the thing of highest priority to the thing of second highest priority to the thing of third highest priority. If in doing so, we spin a clockwise circle from the perspective of looking at it your way, we spin a clockwise circle, that's the R isomer. If in doing so we spin a counterclockwise circle, that's the S isomer. Like if the blue guy were priority number 1, the red guy number 2, and the yellow guy number 3, and going from priority number 1 to priority number 2 to priority number 3, from your perspective, that's a clockwise circle. This would be the R enantiomer. In doing so, if we had to spin a counterclockwise circle, that would be the S enantiomer. And R and S, you're probably saying, why not clockwise or counterclockwise or something? R and S come from the Latin, and you've seen them in other contexts. R is rectum, which has nothing to do with your butt. It means to the right. And S, sinister, has nothing to do with being evil. It just means to the left. And of course, right and left actually make no sense here because we're talking circles. But we have a bias top versus down. So if you start at the top of a circle and go clockwise, you're initially going to the right. If you're starting at the bottom, you'd be going to the left. But we have a top bias. So if you start at the top of a circle, if you're going clockwise, you go to the right. So that's the R isomer. If you go to the left, that's counterclockwise. So that's the S isomer. So, I didn't make it easy for you right from the get-go, but that's okay. Who's this?
Oh, he's coming out, turn around.
Who thinks R? We got some R's. Who thinks S? We got some S's. Who doesn't think? This is S. Therefore, this is R. Simply knowing that this is S and this is the mirror image and it's chiral, it's got to be the other one, R. Here's the deal. Here's our methyl group. It's the group of lowest priority. Iodine, highest priority. Bromine, second. Chlorine, third. Some of you are probably looking at that 1, 2, 3. Ooh, that's clockwise. Well, that's the wrong perspective. The methyl group is coming out at us. There are a couple of ways in which you can do this. With the methyl group coming out at us, and therefore the other three, the tripod going back behind, you can try and take this molecule and manipulate it so as to be in a better position for you to see what's going on. I've been doing this decades and I find that difficult. Here's the way I do it, which isn't to say it's the way you have to do it, but I find this straightforward myself. I leave this molecule alone. I don't try and move three-dimensionally, move the molecule. When I try and make this molecule sort of dance in my head three-dimensionally, it gets all twisted around. So I leave the molecule be. But then I take my mind's eye and put it where it needs to be. The methyl group is coming out at us. So the proper viewpoint of this molecule is on the other side of the whiteboard looking this way. That I'm capable of doing in my little TED head. I put my eye on the other side and I look this way. Doing that and going from iodine to bromine to chlorine. From the point of view of somebody on the other side of the whiteboard looking this way, that's a counterclockwise circle. That makes it S. Here's another thing worth saying that I'm always a little nervous about saying. But I think I heard Jonathan, I think I heard you guys, I heard you guys talking this way. Maybe this is how you were thinking. It's legitimate, but it makes me a little nervous to say it. And that's that the way I wrote this molecule, I oriented it in precisely the wrong way. I've got the group of lowest priority coming towards us. We want the group of lowest priority going behind us. But I've got it coming towards us. In other words, it's the opposite of what the Continental preload system says it's supposed to be. So looking at it in opposite land, yeah, I am going clockwise, therefore it's supposed to be counterclockwise in Continental preload land. Yes. Okay. Here's a molecule. Is it chiral?
Yes.
It is chiral. A lot of people, initially, you might think it's not chiral. It doesn't have four different things. It's got a hydrogen, a bromine, and a carbon, carbon. But you have to look at the entirety of what's bonded to it. What's bonded to this carbon is a hydrogen, a bromine, a methyl group, and an ethyl group. So you have to look at the entirety of what's bonded to that central carbon. So yes, this is a stereogenic carbon. It is therefore going to have a mirror image that's different from itself. It's going to be an enantiomeric. We have to be able to assign an RS designation to it. What's the thing of lowest priority?
Hydrogen.
Hydrogen. This is easy. If hydrogen is one of the four things, it is going to be the thing of lowest priority. It's based on atomic number. You can't have atomic number less than 1. What's the thing of highest priority? Bromine. You go to just the atom bonded to the central carbon. You just look at what's bonded to this carbon. Here a bromine is bonded, here a carbon is bonded, here a carbon is bonded. Bromine has a higher atomic number, priority 1. Now, as far as who's second, I go here, carbon. I go here, carbon. That's a tie. The rules are, we could invent other rules, but the rules are, you keep going until you break the tie. So, since what's bonded to the central carbon is the same thing, you look at what's bonded to this guy now. This guy is bonded to 2 hydrogens and a carbon. This guy is bonded to 3 hydrogens. Well, this guy's carbon beats this guy's third hydrogen. Therefore, this is priority 2, this is priority 3. In this case, I made it easy for you. Is this R or S?
R.
R. This is R. In this case, I drew it so that the group of lowest priority was behind the whiteboard. So I drew it kind of already set up in the proper orientation. So we're looking at it the right way. Hydrogen is behind, going from first to second to third priority. That's spinning a clockwise circle. This is the R enantiomer. Its mirror image would be S. How about got a stereogenic carbon, we've got 4 different things bonded to it. We assign priorities. We've got a hydrogen, that's obviously priority last. Priority number 1 is the bromine, number 2 is the chlorine, number 3 is the carbon. So those are our priorities. If you can take that 3-dimensional thing and manipulate it around and put it in the proper orientation, good for you. The game I play is I put my mind's eye where it needs to be. The hydrogen is above, so I'm lying on my back looking straight up at this thing. And going from 1, which is out here, to 2, which is here, to 3, which is here. That's a counterclockwise circle from the perspective of someone looking this way. That makes that the S in engineering. If what we're doing here isn't feeling good to you, one option that always exists, build it. Then you have something tangible in your hand. You can actually hold it in your hand. Put the group of lowest priority, literally physically behind, right in front of your eyes. The other 3 things will be popping out at you. Spin your circle to get your R or your S. So how about this one, R or S?
I can't read that.
You don't have to read that. What can't you read?
Top. Is that an 8?
That looks like an 8.
That looks like an 8.
It looks like an 8.
Looks like my hand, right?
What does it have to be?
Okay, now I don't know. Yeah.
There's only one thing that can be, and that is a 2. There's only one thing that can be, and that is a 3. So yeah, I know I write sloppy from time to time, but give me crap when it counts. not when it's irrelevant. You guys know carbon needs 4 bonds. This guy, carbon, therefore has to have 2 hydrogens. This guy has to have 3 hydrogens. Okay. R or S?
S.
Not both. Neither.
Because it's
Yeah. Yeah. The question, is it R or S, makes no sense. This is not a chiral molecule. There is no stereogenic carbon here. Ethyl group, it doesn't have 4 different things bonded to it. So it's neither R nor S, the whole concept doesn't apply. Oh my gosh. Here's another common way to show 3-dimensionality. We've indicated that this concept of enantiomerism applies to virtually all biological molecules. It famously applies to the sugars. Most sugars, even as simple a sugar as a glucose molecule, have multiple stereogenic carbons. Glucose has 4 different stereogenic carbons in it. So how many different isomers of that do you think there are? Those of you that have a little statistics in your mind. You have 4 possibilities. Each one could be R or S. The total number of options would therefore be If it's either or thing, like flipping a coin, heads or tails, if there are two possibilities and you have four things with those two possibilities, 2 to the 2 raised to the power equal to the number of things that have that possibility. In this case, 2 to the 4, which would be 16. There are 16 different isomers in this. So I mean, that right there tells you the importance of this. 16 different isomers in the sucker. All stereoisomers of each other. All composed of the same atoms. All bonded in the same order. It's just the three-dimensionality that's different. Anyway, so this planet's first sugar chemist was a person named E.O. Fisher. He was the first to elucidate the structure of any sugar, and he realized, holy cow, look at all these stereogenic carbons, this is going to be a pain in the butt. He says, like, there's no way I'm wedging and dashing all this stuff. It would be a humongously complex looking structure if I had all these wedges and dashes around all these stereogenic carbons, these big sugar molecules. So he invented a different way of showing the three-dimensionality. And we honor him by calling them Fisher projections. A Fisher projection looks like this. I'm done. The idea is that here is our central carbon, and here are the four things bonded to that central carbon. By convention. Now remember, a tetrahedron, you got a B, and then you got an inverted perpendicular B. By convention, the two V's, the things to the right and left, are thought of as coming out at us, and the things above and below are thought of as going back behind. Two ways in which I keep that straight, even to this day, just to make sure. I think of pinching your nose. If you want to pinch your nose so that you can't breathe out of it, you pinch it this way. It doesn't do much good to pinch it this way. You pinch it this way. So think of this coming out and pinching your nose. So these have to come out. These can't be coming out. These have to come out. The other way I keep it straight is if we were to draw this using wedges and dashes, if the things to the right and left are coming out at us, those would be our wedges. And if the things above and below are going back behind the plane of the whiteboard, those would be our dashes. And then I think of a bow tie. We wear bow ties like this. We don't wear bow ties like this. Okay. R or S? There's some muslins.
S.
This is S. The group of lowest priority, of course, is the hydrogen. If it's there, it's always going to be lowest priority. Highest priority, this would be 2, this would be 3. And I made it easy on you. Because I wrote the Fisher projection with the group of lowest priority in the back already. Because above and below are going behind. So the hydrogen is the back. We're looking at it this way, with the ethyl group and the bromine coming out at us. Bromine to ethyl to methyl. That's a counterclockwise circle from a person looking that way. That makes it S. about this one? That's R. Priority 4, priority 1, priority 2, priority 3. This time, wah wah wah, pinching our nose, the hydrogen is in front of us. So our mind's eye is in the back, looking this way. The ethyl group is also out here. And going from bromine to ethyl to methyl, that's a clockwise circle from the perspective of someone on the other side of the whiteboard looking out this way. That makes it R. So what's the relationship between these two molecules? Say it. They're a pair of enantiomers. Do they look like mirror images of each other? I mean, you know, not really. They're not drawn to show mirror images of each other. You know, if I hold that up to a mirror, I don't see that specifically. But I can rotate this so that it is the mirror image of that. So yes, they are mirror images of each other, even though it's not kind of obvious that you see it that way. But here's one thing you can do with Fisher projections that's very helpful. You can do it with the wedge and dashes too, but I'll make sure I give you a strong caveat on that. If I look at this Fisher projection and I look at this Fisher projection, the ethyl group I have in the same place, I'm showing it to the left. The methyl group I have in the same place, I'm showing it down. What I've done is switch the bromine and the hydrogen. Take any Fisher projection, switch any two things, you've got the enantiomer. If you take that enantiomer and then switch any two things, what do you have? Well, you would have the enantiomer of that enantiomer, which is the original compound. So take this, switch any two things, I switch the hydrogen and the bromine, switch any two things, I have the enantiomer. If I take this, switch any two things, I'm back to this compound. If I take this, switch any two things, I'm back to this compound. So I can look at any Fisher projection, any two Fisher projections. If I can get from one to the other by switching any two things, they must be a pair of enantiomers. If I can get from one to the other by switching twice, making two switches, they must be the same compound. Suppose I play this game and I end up making 7 switches to get from one to the other. What do I have? I have a pair of enantiomers. One switch gives me the enantiomers, 2 brings back the original compound. A third switch will give me the enantiomer, a fourth brings back the original compound. And so on. Does that make sense? Of course it does. It's chemistry. What's the relationship between these two guys? I don't know, let's find out. Here's a Fisher projection, there's a Fisher projection. I can assign R and S, and we'll do that. But before I assign R or S, as far as just whether they're a pair of enantiomers, I can see that I have the iodine in the same place. I have the fluorine in the same place. I've made one switch. All I've done is switch the chlorine and the bromine. That makes them a pair of enantiomers. So which ones are?
The right one. One on the right.
This one is R. Which automatically makes that one S. If you're seeing that, good for you. If you're not seeing that, play with bonds. What's their relationship? Or you can assign S or R. And you can play the switch game. Let's do S and R first. What do you got here?
Should be S.
I'm hearing mainly R.
It should be S.
I'm not very happy about hearing mainly R. I'd
It
be
should be
happier
S
if people
because
said
F is
S.
going back.
This is a group of lowest priority. So priority-wise, this is lowest, this is highest, 2, 3. So it's actually set up for you. Fluorine is in the back, these things coming out at us, going from 1 to 2 to 3, that's counterclockwise from this perspective, that's S. What's this one? R. Group of lowest priority, it's coming out at us, so we're behind the plane of blackboard going this way, going from 1 to 2 to 3. Wait a second. Oh, 1 to 2 to 3. From the perspective of being on the other side, that makes us R. Since we're out of time, playing the switch game, let's see. Well, you want the fluorine to be over here. It's here. So let's switch these guys. Fluorine and chlorine. That puts fluorine in the right spot. We just made a switch. Well, we don't want chlorine down there. We want chlorine up here. So let's switch the chlorine with the bromine. We just made a second switch. We now have the fluorine and the chlorine where they belong. So we need the iodine and bromine on in the right spot. So we switch them. Put the bromine up here, the iodine down here. I just made 3 switches. Take myself from here to here. An odd number of switches means they have to be a pair of enantiomers. That doesn't tell you which one is R or S, but it tells you it's a pair of enantiomers.